start recording. Okay, so the 70 kilogram stunt person attached to a bungee cord, unstretched length is 15 meters. The bridge spans the river at 50 meters, and when they changed the numbers, I think. When he stops, the cord has a stretched length of 44 meters. So unstretched, 15. Stretched out, 44. Maybe they didn't change the numbers. Anyway, doesn't matter. Treat the stunt person as a point mass, disregard the weight of the bungee cord. Assume the spring constant of the bungee cord is 71.8 newtons per meter. What's the total potential energy relative to the water when he stops falling? So when the stunt person ends up here, how much potential energy does he have? Total. This is where we're going to get into a conversation about net and gross, or net and total. So the first thing we need to know, well, let's do the easy one first, shall we? Let's talk about this. So potential energy total in this case is going to equal potential energy due to gravity plus potential energy due to elastic, PEG and P. And we know that this is really simple, mass, gravity, height. And that the potential energy due to elastic is a little bit different. 1/2 k x squared. Okay. That's our potential energy total. So mass, gravity, height, well, we're told that the stunt person weighs 70 kilograms. So we have 70 kg times 9.81 meters per second squared. At the point when the stunt man stops above the river, how many meters above the river is he? 6. So he's got 6 meters left to fall, 6.0 meters. So that will give us our gravitational. Now, 1/2 k, we're given k. We're told that k is 71.8 newtons per meter. I said that x was a distance, but I didn't tell you what the distance was yet. So think about stretching a rubber band. If you stretch it this far, does that have the same amount of force as if you stretch it this far? The further you pull that thing, the more force it's going to snap back with. X is the difference in deformed and undeformed length. So let's make a note of that. X equals deformed minus undeformed length. So in this case, that's 44 minus 15. I'm going to shrink all of this. 44 meters minus 15 meters squared. Okay, so let's plug in some raw numbers, and I want you to actually first arrive at the values for this. And then we're going to talk about how your book does it and the issue that I want to see if any of you have with that. So go ahead and get some numbers. Do you have something like that? Okay. Much more potential gravitational, or much more potential elastic energy than potential gravitational. Now, here's what your book does. It adds these two together and gets a potential energy total of 34312.1 joules, total potential energy. Does anybody have any issues with that? The gravitational, if we think of energy as the ability to do work and work as a vector sum. Now, let's not forget here that I'm a biologist who teaches physics. So the people who wrote this were PhDs in physics who teach at universities. I'm quite sure they know a whole lot more than I do, but I still quibble with this one. Yeah, the total, if we ignore direction, is 34,000. Obviously, sig figs are wrong here. It'd be what, 3.4 times 10 to the 1, 2, 3, 4. But one of those potential energies would do work on the stuntman down. One of those potential energies would do work on the stuntman up. I have a problem with adding those together. Do you see the problem? Some of you obviously do, and some of you are squinting your eyebrows at me like I'm crazy, which I'm used to. So this is where I quibble, and what I keep thinking, I keep meaning to write the textbook. They've probably fixed this in a subsequent edition, or I'm just crazy. If we think about potential energy net,
This is a subsequent edition.
it is, I know they haven't fixed it yet. That's okay, there's still hope. This is 2006. They've got 12 years of editions that I haven't seen. But I wonder, so you can completely disregard what I'm saying here, or go talk to an engineer. I wonder if there's room for PE net, which would reflect that difference, just like net force reflects the fact that a force up and a force down doesn't equal the sum of the magnitudes, it equals the difference. And to, again, to quibble, it seems to me that there ought to be room for, so what would that be? That would be the 30,000 minus the 4120. So, I might say that the net potential energy on the individual is something like that. I don't know. Does that seem crazy? Maybe. Maybe not. Anyway, all the problems on 4D are assigned. So how many are in the paper textbook? Just 3? Okay, and there are 3 in the electronics, so we're good.